process. So the contact process we can identify is the production of making sulfur dioxide. And so it does this by converting sulfur dioxide into sulfur trioxide. And so this is like our main reversible reaction, which is at the heart of the process. And it can then also convert sulfur trioxide then into the sulfuric acid, which will be highly concentrated. So it's mainly like a two-step process in which we first have to start off with sulfur dioxide to sulfur trioxide, and then after sulfur trioxide going into the concentrated sulfuric acid. So our first step is making the sulfur dioxide in order to start off with that. And so it's almost then becomes like a three-step process. So to start off with, we got to make the sulfur dioxide, which is done either by burning sulfur in an excess of air or by heating sulfide ores, such as pyrite, in an excess of air. So the way which we can do this by burning sulfur in an excess of air is if we take sulfur gas, so S2, and we burn that in oxygen, so O2. We can then that can then help us to produce sulfur dioxide. And then our other method is using the sulfide ores like pyrite. So we can use a ratio of 4:11 of FeS2 to oxygen. And then that can produce a ratio of 2:8 or 1:4 of Fe2O3 and our sulfur dioxide. And so in either case, an excess of air or oxygen is going to be used so that the sulfur dioxide which is produced is already then mixed in with oxygen, which can then be used for the next stage of the reaction, which is obviously making then the sulfur trioxide. So our next part of the process is then converting the sulfur dioxide into sulfur trioxide. And so this is an equilibrium reversible reaction. So we can apply Le Chatelier's principles concepts to this. And so the formation of sulfur trioxide is also an exothermic reaction. And so we use a vanadium oxide catalyst here as well in order to improve and increase the rate of conversion. So this reaction goes in a reaction of sulfur dioxide, a ratio of 2:1 of sulfur dioxide to oxygen. However, we can use excess oxygen gas because it can just be atmospheric oxygen. And then that will produce the sulfur trioxide in a ratio of 2:1:2 of sulfur dioxide to oxygen to sulfur trioxide. And as said before, this reaction will also give off heat because it is an exothermic reaction. And so our delta H value for this would be negative. And so for this particular reaction, the delta H value is actually negative 196 kilojoules per mole. However, you don't need to remember this for the exam. That just helps to show that it's an exothermic reaction. And so we then, after doing this, need to convert the sulfur trioxide into sulfuric acid. And so this simply can't just be done by adding water to the sulfur trioxide, because the reaction would be so uncontrollable that it would create fog of sulfuric acid, and it would be like a sulfuric acid gas instead of the concentrated sulfuric acid. And so the sulfur trioxide is first dissolved into concentrated sulfuric acid to create what we call oleum. And so this is done in a reaction where we take sulfuric acid and we add it to sulfur trioxide to then make fuming sulfuric acid, which is liquid sulfuric acid, which is called oleum. And so this can then be safely reacted with water to then produce the concentrated sulfuric acid, which is twice as much as you originally used to make the fuming sulfuric acid or the oleum. And so you're basically then doubling the reaction product and doubling the efficiency. And so this then goes as oleum plus water, which will make a ratio of 1:2 of oleum to sulfuric acid. And so that sulfuric acid will be as a liquid. And so when we consider the reaction conditions for the contact process, we need to consider the proportions of sulfur dioxide and oxygen. So the mixture of sulfur dioxide and oxygen going into the reactor is going to be in equal proportions by volume. And so this is because we then relate this back to Avogadro's law again, which says that equal volumes of gases at the same temperature and pressure are going to contain equal numbers of molecules. And so this basically means that the gases are going into the reactor in a ratio of 1 molecule of sulfur dioxide to 1 molecule of oxygen. And so there's going to be an excess of oxygen relative to the proportions demanded by the equation anyways, because we're using atmospheric oxygen as air. So that basically means that we only need to use the necessities of sulfur dioxide whilst we have as much oxygen available for the reaction as we need. And so that's for the first step of the process. And then, so for the next part of the process, we need to then consider how we can apply Le Chatelier's principle to this, because Le Chatelier's principle can then help us to maximize the rate of the reaction, because this is a reversible reaction. So according to Le Chatelier's principle, increasing the concentration of oxygen in the mixture causes the position of equilibrium to shift towards the right. And so this is because we have increasing the concentration of reactants forces the reaction to the right to make more products. And so since the oxygen comes from the air, this is a very cheap way of increasing the concentration of sulfur dioxide into sulfur trioxide, because if we're performing this reaction in an excess of oxygen, we obviously have continuous supply of oxygen concentration into this, so it's very inexpensive to increase that rate of reaction. And so we could consider, why not use an even higher proportion of oxygen? Why not make it extremely concentrated? And so this is very easy to see if you take an extreme case. So like supposing if you have 1 million molecules of oxygen to every molecule of sulfur dioxide. And so the equilibrium is going to be very tipped strongly towards producing sulfur trioxide, because virtually every single molecule of sulfur dioxide will be converted into sulfur trioxide. And so this sounds great, but you aren't going to produce much sulfur trioxide every day, because the vast majority of what you are passing over the catalyst is oxygen. And so if you're putting mostly just oxygen over the catalyst, it's not actually going to have any sulfur dioxide to react with, and so nothing's actually going to be produced. And so by increasing the proportion of oxygen, you can obviously increase the percentage of sulfur dioxide converted, but at the same time, you can also decrease the total amount of sulfur trioxide which is made each day. And so the 1-to-1 mixture turns out to actually then give the best possible overall yield of sulfur trioxide. And so hence why the 1-to-1 ratio is preferred as opposed to that extreme ratio. So next we need to consider the temperature for this reaction with an equilibrium consideration, but also with a rate consideration, and then the compromise which we come to. So you need to shift the position of the equilibrium as far possible to the right in order to maximize the possible amount of sulfur trioxide in the equilibrium mixture. And so the forward reaction, or the production of sulfur trioxide, we know is an exothermic reaction because it has that negative delta H value. And so, according to Le Chatelier's principle, we know that the rate of reaction of an exothermic reaction will be favoured if you lower the temperature. And so we remember this is because in an exothermic reaction, heat is being produced, so we consider heat to be like a product. So if we're taking heat out of a system or taking product out of a system, in the case of taking heat out, it's like cooling the system down. And so if we were to take product out, we would force the reaction in the forward direction to replace product that is lost, and hence producing more heat to counteract that change. And so in order to get as much sulfur trioxide as possible in the equilibrium mixture, you need as low of a temperature as possible. But we want to use, again, like in our previous situation where we looked at the Haber process, we want to use a temperature that is 400 to 450 degrees Celsius, which we know we don't consider to be a low temperature. However, industrially, that's considered a low temperature due to the reaction's rate of reaction. And so we remember the lower the temperature you use, the slower the reaction becomes. And so the manufacturer wants to try and produce as much sulfur trioxide as possible per day. So it makes no sense to try and achieve an equilibrium mixture which contains a very high proportion of sulfur trioxide if it's going to take, again, several years to achieve that equilibrium. And so in order to have the gases reach equilibrium within a very short amount of time, whilst maximizing that forward reaction and maximizing the amount of sulfur trioxide produced in that equilibrium mixture, you'll need the gases to reach the equilibrium in a short amount of time so that they can be in contact with the catalyst in the reactor. So the compromise for this is producing a reaction at 400 to 450 degrees Celsius, which is our compromise temperature to then produce a fairly high proportion of sulfur trioxide in the equilibrium mixture, but also then in a very short amount of time. We also then need to consider the pressure which will be used for this system. And so the pressure which is used for this system is going to be based on that there is 3 molecules on the left side of the equation, but only 2 on the right. And so according to Le Chatelier's principle, we can remember and recall that if you are increasing the pressure of the system, it's going to respond by favouring the side of the reaction which has the least moles of gas. So we've got 3 on the left-hand side and 2 on the right. We want to increase the pressure of this system so that it favours the right side of the reaction where the products are located, because the gas wants to take up the side with the least moles of gas because there is less space due to the higher pressure. And so in order to get as much sulfur trioxide as possible in the equilibrium mixture, you need as high pressure as possible. Because remember, high pressures can also increase the rate of reaction. However, this reaction is actually done at pressures close to atmospheric pressure. And so you may wonder, why would we use atmospheric pressure if we want to maximize the rate of reaction and the equilibrium concentration? And so this is because of an economic consideration. So even at very low pressures, there is a 99.5% conversion rate of sulfur dioxide into sulfur trioxide. And so the very small improvement that you could achieve by increasing the pressure of the system just isn't worth the expense of producing those high pressures. So hence, we settle with atmospheric pressure, at which you don't need to actually apply any pressure to the system. Finally, we need to consider the catalyst which is used for this system. So This is going to consider both the equilibrium and the rate of reaction. So we know that the catalyst is going to have no effect whatsoever on our position of equilibrium. However, we do know that adding a catalyst is going to speed up the rate at which that equilibrium is achieved. We know it's not going to produce any greater percentage of sulfur trioxide in the equilibrium mixture, but if we do achieve that equilibrium quicker, we can obviously then go on to produce more if we're doing it at a faster rate. However, when we consider rate, in the absence of a catalyst, this reaction is basically so slow that virtually no reaction is going to happen in any sensible time. So the catalyst is going to ensure that the reaction is fast enough for a dynamic equilibrium to be set up within a very short amount of time, so that the gases are actually reactive in the reactor. And so this is the reason why we then use our vanadium oxide catalyst. So that's our production of sulfuric acid.